Okay, very good afternoon to all. So today I'll be talking about how to really deal with the measurements from a mass spectrometer. So how basically we analyze the data. So before going into the details of the analysis, let's have some background information which is important to really to deal with the data. Yeah, myself, Dr. Dhanya, and I'm working as a scientist at a space physics laboratory in Vikram Sarabhai Space Center. So basically, I work with the mass spectrometry technique as well as science analysis of its data, so which we will eventually discuss. So what is basically a mass spectrometer? Mass spectrometer are basically an instrument. As the name suggests, they are mass. So basically, they determine mass. So there is a small change in the terminology. Instead of simple mass, we say it determine mass to charge ratio. So basically, they determine M by Z. This is why this term comes. Is we will see later, soon. This because the technique involved in mass spectrometry is by ionizing a sample, which is basically a gas, which is like say we want to determine what is present in the air around us. We are sitting in a room now, so what all elements are present in the air around us, which is basically we know molecules. They are molecules and atoms. So this, in order to sample this gas, first this gas is ionized. So, and then once we ionize, their electrons are removed from a molecule or an atom. Then it becomes a positively charged ion. So further, these ions are subjected to detection. So that's where this mass to charge ratio come into the picture. So that is what it is written here. They get converted to ions, and basically because any technique involves separating them based on electric field. Most of the techniques we use cannot really directly deal with the neutral gas or molecule or atoms. We need to control them by applying electric or magnetic field. For an atom or a molecule to response to electric or magnetic field, they have to be ions. They have to have charge. That's why we ionize them. So based on mass to charge ratio, we detect the ions, and then back once we detect the ions, then we trace back which is the parent atom or molecule. And in this process, we find there how much of that quantity is present also. Not only what are present and how much of them is present in the sample. So for this purpose, every mass spectrometer will have a source to ionize the sample, then some technique to find the mass, and to separate the mass basically, and finally to detect them, like we say a detector. So what will be the output of mass spectrometer? They are basically a mass spectrum. We call them as mass spectrum, where x-axis will be mass to charge ratio and y-axis will be their intensity, we can say. So you can see here certain lines are shown here corresponding to certain M by Z, which are identified as some organic molecules here, which are shown here. Similarly, here on the right side also some M by Z's are shown, and with their abundance we can find the certain peaks people have identified it is because of certain elements. So that this is the way it is used. And now where all are it is used? Mass spectrometers are used in laboratories to identify. They have applications in various fields. They identify the composition of any sample. It is used in medical research and pharmaceutical analysis and biophysical applications, etc. So mass spectrometer is a powerful tool which can identify what is a constituent in such samples. And we use them for another purpose, where we want to measure the neutral atoms or molecules in the atmosphere of a planetary object. So for that purpose, we use mass spectrometer. Since we have to measure, in order to measure the atmosphere of a planetary object, we have to go there, because mass spectrometer takes the gas inside and then they detect what is a composition. So that such measurements are called in situ. You would have already have some lectures on in situ. So in situ refers to being in the medium. So they measure the medium where they are situated. So in order to have such measurements of planetary object, we need to send the mass spectrometer there. So that's why we use them on space missions. And such a few examples are, or such missions are, from the, in the case of moon, starting from the Apollo era, that is 1970s, we have been sending mass spectrometer. And then our own Indian mission Chandrayaan 1, and then later another mission from NASA called LADI, and then Chandrayaan 2. On Chandrayaan 2 we have a mass spectrometer. And if we consider our nearest near planet, or nearest near planet, neighboring planet, we can say, we have Mars orbiter mission, and then even from NASA. Then for Venus, again in 1970s, Pioneer Venus mission carried mass spectrometer. And this mission, probably you would have heard of it, as a popular mission which traced a comet, which was like chasing a comet and then measuring. So there also mass spectrometer is sent. And to another planet, Mercury, mass spectrometer. So these are just a sample examples. There are other missions like to other planets also, and other asteroid sort of bodies also, mass spectrometer have been sent. Now, in Indian scenario, where we have used. So in Chandrayaan 1, which was launched in 2018, you can see this Chandrayaan 1 satellite schematic. And there was a moon impact probe here, this box. And this box got separated from the satellite when it reached near the moon. And then it fell on moon. So on the way, it made measurements. So on that, we had a mass spectrometer, which is called Chandra's Altitudinal Composition Explorer, in brief, CHASE. And as a follow-up of like CHASE, another mission was Mars Orbiter mission, which actually was launched in 2013. And in like in Chandrayaan 1, CHASE measured the atmosphere of moon while from a given height till it reached the surface. In the case of Mars, the mass spectrometer was used to study the or measure the atmosphere of Mars at above certain height till where the spacecraft can go. And that experiment is called MENGA, which is Mass Exospheric Neutron Composition Analyzer. Basically, this was a follow-up of CHASE. And next, we got opportunity on Chandrayaan 2 orbiter, where a similar mass spectrometer was flown. This time, this is not on an impactor. This is on an orbiter. So an impactor means it will, from a given altitude, it got separated and then it fell on ground. So that much only time only it can measure. Whereas on an orbiter, this mass spectrometer keep on moving around moon, keep on moving, and on during all its passage, it takes keep on taking data or making samples, and then understand what is the composition of the moon atmosphere. So this is like more like a more measurement or more continuous observation, we say. Now, like in the case study, as a data analysis demonstration, I have chosen CHASE 2 data because, as I mentioned, it has more measurements in every orbit it measures. So that way we have big measures the total whatever comes inside the mass spectrometer, the total current, or we say total pressure it measures. After that, these atoms or molecules are mass analyzed, and their last what we get is a pressure corresponding to a given m/q, so which we call as partial pressure, whereas the Bayard Alpert gauge measures the total pressure. And then the detectors used a combination of Faraday cup and channel electron multiplier. And then in the ionizer, we employ electron impact ionization technique, which means that when a sample enters the mass spectrometer, electrons impact on the sample and ionizes. A beam of electron impact on the sample and ionizes them. Now, this is the detail of the technique, where we can see that this is like more details in the ionizer, which is zoomed in here. Ionizer consists of filament, and which is a dual filament. Two filaments are there, and which emit the electron, which will impact on the neutrals and then generate ions. And the Bayer gauge measures the total pressure. So this all happens here. Once these are ionized, these ion passes through an area which is the mass analyzer, which is called a quadruple mass analyzer. You can see there are 4 rods here. 1, 2, 3, 4. So it's a quadruple rod sitting, and then we apply AC and DC voltage across this quadruple rods. So basically you can see here, these are the 4 rods and a combination of DC and AC voltage. So because of which, for a given AC and DC combination, these ions oscillate, and certain ions only will be allowed to pass through. Certain ions of a given mass to charge ratio, they will only be allowed to pass through. So the voltage will decide in a way the mass which will finally will be filtered in. So, and based on the mass range, I said initially 100 to 300, 1 to 300 AMU, we have to apply voltages in that range so that 1 AMU to 300 AMU will be filtered in steps. So for a given voltage, 1 AMU will be allowed in, next voltage 2 AMU will be allowed in, like that. So they sort the ion with respect to their mass to charge ratio. Finally, they fall on the detector, and in the detector, channel electromultiplier will amplify the signal, and we get the current output, which is calibrated to basically show here as current as a function of mass to charge. You can see certain peaks here. So we can say at 18, this is something like 18 AMU. This is the water, peak corresponding to water. 17 AMU will be OH, and then 1 AMU H, 2 AMU H2 molecule. And at 28 AMU, it can be molecular nitrogen or carbon monoxide, like that. So based on mass to charge ratio, we identify the elements and then quantify how much of them are present. So chase 2 basically have 2 modes of operation. Actually, there are 3 modes. So one is used as an engineering mode. So scientifically, it has mass sweep and trend mode. In the mass sweep mode, it keep on scanning the species, and we get like a partial pressure for a given mass to charge ratio. What is the quantity, which is the partial pressure. So, and we can change the mass range, and we can even change the rate at which this sampling is done, etc. So these are all programmable features built into this. And then trend mode, in trend mode, what we do is, instead of scanning from 1 to 300 AMU, you select a few species. We can choose up to 15 species and track only them. So if suppose I wanted to know how oxygen varies in the during measurement, so only oxygen, the AMU corresponding to oxygen only will be scanned. Like that, you can choose the species. So now if you see the heritage, like Chase 2 is a follow-up of Chase 1 and MENCA, where we have all modes of operations are and programmable features are there compared to MENCA. Like it is more like Mars orbiter mission payload, whereas in the case of Chase, it was basically, since it was an impactor, there were no programmability here in the mass range also, as well as it was operating only in mass sweep mode. So now let us look at the data part. Data. So now what is the science data from Chase 2? Basically, we get in the science data, as I mentioned, a pressure corresponding to each mass by charge bin. So which is called as the partial pressure. So partially because it corresponds to given mass to charge particle. So, and as a virtue of the scanning from corresponding to 1 to 300 AMU, we have mass to charge ratio up to that, and then it's their relative abundance. So which is called as a mass spectrum. So this is a spectrum from Chase 2 in orbit. It is taken on 20th of 2019, September 20. So when Chandrayaan 2 was at an altitude of 88 kilometers. You can see here x-axis is the mass. Actually, it is mass per charge, and then rho partial pressure. So I see certain peaks here. So these are corresponding to certain species. So which is identification based on their like 20 AMU. What is that? 40 AMU, what is that? That we do based on our knowledge of the lunar environment, expected species in the lunar environment, and also another parameter called outgassing. Like in space, any material will start giving out many of the volatiles in it. So they also can contribute to our measurement. So we have to eliminate such other sources and then narrow down to which is seen. Then in addition to this raw partial pressure, we get in the data a housekeeping parameter. Like I was mentioning, there is a filament, and then we apply voltage across a quadrupole rod, etc. So filament voltage, filament current, these are important parameters, because if filament is healthy only, ionization will happen. That is the starting point of the measurement. And there are several operating parameters, like we can choose the mass range, we can change the detector voltage. So these kind of things are, these data also comes along with the science data. So this is the in-orbit observation, one sample where we have, it is like 12th of October 2019. We can see it's a spectrum in the lunar orbit. So we have like 18 AMU. We have identified a certain molecules here which are marked here, like water, then 28 AMU, then 44 carbon dioxide. And we already have analyzed argon 40, which is, will appear at 40 AMU channel. And that is the global distribution argon 40 we have published. And this is the housekeeping parameters, which I was telling, which comes along with the science data. You can see that there are certain power supply voltage, voltages, temperatures, current. So these are the parameters which comes along with the science data, which you can find once in the, when you start downloading the data, these kind of parameters also come, like filament voltage, filament resistance, these kind of things. Now, what kind of ones? Okay, we have the partial pressure, and then corresponding to each mass by Q channel, we can say that this mass M by Q is binned into 1 AMU bins. So now what all things have to be done? So in order to own the data, in order to know that, we need to, I showed here, like this is what, it could be water, or it could be N2 at 28 AMU. How sure we are? Basically, we do certain process at lab, which is called the calibration. In the calibration, we insert known gas and then see whether they appear, the peak, we can say the spectrum, appears at the expected mass position. Suppose you insert argon 40 gas, we should expect a peak at 40 AMU. That is a way. So this is the a mass calibration with a residual gas in a vacuum chamber, where we have not inserted any gas. In a vacuum chamber, there will be already air. How much we evacuate also, there will be residual air in the vacuum chamber, and there will be water absorbed in the steel, because this vacuum chamber is made up of steel. There will be joints everywhere, so their water will be get absorbed, because we are living on earth where enough moisture is there. So once in vacuum, this moisture starts oozing out, and then we will detect them also. So this is what is done here. You can see mass per charge as x-axis and ion current on y-axis. Certain peaks are seen. If you zoom in here, you can find that we have peak at 18 AMU, 17 AMU, 16 AMU, then 1, 2, like that. So this is on Earth, we have abundant, N2 is there, then O2, CO2, all are there in air. And then in addition, this water is coming from the moisture in the air. And now, like when we are, another experiment is where we demonstrate the sensitivity, because we can measure up to, using the mass spectrometer, we can measure up to 10 to the minus 14 torr. Torr is the units which we use to denote how much it can measure. That is basically the pressure. So 760 torr is actually 1 atmospheric pressure, or we say 1 bar. So this in terms of torr, we say that we can go even up to 10 to the minus 14 torr. That much low, which is almost equal to 100 particles per centimeter cube. That much low density. So at 10 to the minus 14 torr, this we have demonstrated in the laboratory using a special facility at RRCAT, which is situated in Indore. So during Mars mission time, so our mass spectrometer is able to see signals up to 10 to the minus 14. And this is the kind of noise level. So this establishes the sensitivity. So this is a part of the calibration. Now when we come to data processing. So now first we have our first product is the spectrum. So in the spectrum, mass spectrum basically, like each, like we have seen several peaks here. So as an example, if you see this, it's a peak. Each peak is constituted by 9 points, which we call as 9 samples. This is because the mass spectrometer scans each AMU bin in steps of 9. So basically, we can say the one step corresponds to roughly 0.1 AMU. So if you have one AMU, this is the way the step goes. Finally, the voltage, what it happens is for one AMU scanning, there will be a given voltage. So our system will start scanning from some voltages before the specified value and beyond the specified value. So it is like a continuous scanning. So initially we will not start seeing the signal, and as we approach close to the expected voltage corresponding to that mass, we start seeing increase in the signal and finally decrease beyond that. So this is something like an ideal case. 9 samples, 9 steps of voltage scanning will constitute one peak. In reality, so this is one mass spectra. In reality, if we can see that this is the kind of sample. So each circle corresponds to a sample. So here also this is this peak is corresponding to 18 AMU and this is corresponding to 17 AMU. But you can see here that this peak of position is shifted. 18 AMU is here, whereas this has come before that. So this peak has to be shifted slightly to come at 18 AMU position. So what this means is that in space, when we made the measurements, we observed certain mass shift. So this mass shift is clearly seen in this 18 AMU and similarly 17 AMU. 17 AMU peak is coming here. Actually, it should have been here. So this is not only with this mass range, in all other mass range, like if you see 28 AMU group, peak is coming here. Similarly, we can say 44 AMU, which is coming here, like that. 56 AMU peak is here. So in that way, there is a mass shift. This is one observation. And another is the shape. We told that ideally, we should get a peak like this, yeah, like a low, high, and then it falls. So this is a sort of an ideal peak. But this is not the case always. We do see different peak shapes. You can see there is a like a kink before the peak, and this is after the peak, and then like even a like a reduction in signal strength, like that. So there are several different types of peaks we observe in space. So these are like shown as examples, and there are some negative values also comes into the when we make the measurements. So in order to deal with this, like what is a good quality data? A good quality data is something like out of the 9 samples, 4 samples should follow an increasing pattern, 5th sample should be at the peak, and the remaining should show a fall off. This is a good quality peak, and the peak should appear at the expected mass position. So we, in order to decide anything which deviates from this pattern, we have developed an algorithm which is called a peak filtering algorithm, where mass shift we can account for. After that, we assess what is the quality of the peak and then filter out the peak. Only take the good quality peaks for later analysis. So this is what is done in the algorithm, because we have few data set, large data set. This manual verification become difficult. So we have used this criteria. And first we need to understand how much it is shifted and then correct for it. Then see the quality of the peak, and then based on the assessment, raise suitable flags. Like if all 9 points constitute a good peak, then it will be 9-point qualified. Whereas suppose 2 points are outside this peak, then it is 7-point qualified. Only if a peak is constituted by 1, 2, 3, 4, 5 samples, then it is called a 5-point peak. So generally we use like a 7-point qualified peak for detailed analysis. So these are the details of the algorithm. So this is the final data. After this is like a date and time. This is shows date, then like year, month, day, hour, minute, second, and then which mass bin, and then what is the mass shift observed and what is the partial pressure. Once we correct for the mass shift and then identify the qualified peak, Then we use the peak value for later analysis. So in 18 AMU, this value, this particular is, which is a peak value, this is something like 7 into my 10 to the minus 6. This value will be used for later analysis. So this is the like validation of the algorithm. And finally, this is an example of actual peak, and this is the corrected peak. This is what we observed actual. So this is a mass shift corrected peak. So first step is application of this algorithm on the data. After that, we get the peak partial pressure versus mass by charge. Then what we do is we have other correction factors to apply to this data, which are called a quadruple mass discrimination, detector gain, and normalization. Let us see what are they. And like detector gain, which is called as channel, detector is channel electron multiplier. So it is called a CEM gain correction also. Actually, because we are using CEM, any signal is amplified. We are, whatever signal we get at the output is an amplified version of what is really detected. So we have to correct for the gain. And once we correct for the gain, if it is uniform throughout all mass channels, it is a one factor. But whereas this gain is a mass dependent factor, which we have calibrated in the laboratory. Actually, lighter masses, they are more amplified compared to heavier species. So this is shows the laboratory calibration where mass per charge versus detector gain. You can see that for a given this is each color indicates a given bias voltage of the detector. You can see that for any given bias voltage, say we take red, heavier masses, the lighter masses, the gain is more compared to the heavier masses. So this mass dependent gain we have to correct. That is one step. Another step is quadruple mass discrimination factor. That is nothing but when the masses pass through the quadruple road, between the four roads, there is also a mass dependent efficiency come. Lighter ions will easily pass through compared to heavier ions. So there will be lower or say de-emphasis of heavier atoms or heavier ions. This is because of the fringing field effect at the quadruple end of the quadruple rods, where heavier ions will get trapped. So this mass dependent correction for this quadruple factor also we have arrived at the laboratory based on laboratory calibration. And then finally is the normalization. For normalization, we use the total pressure. What does it mean is when the ions or atoms enter our mass spectrometer, at the ionizer, these are ionized, and the total current is measured by the Baird-Alpert gauge sitting at the ionizer. After that, they pass through quadruple rods and reach the detector. These all have certain efficiency factor where these atoms, molecules can get deflected away. Some molecules cannot reach the detector. Those kind of things can happen. So once we have the total mass spectrum, if we add partial pressure of all the species and compare with the total pressure, there is a difference. Sum of partial pressure is always less than the total pressure. So that means there is certain efficiency involved. So we divide by the sum of partial pressures, divide by the total pressure, and find the efficiency and use it to multiply the partial pressure data. So this is called the normalization factor. And once we have this corrected partial pressures, then we can find the number density. Now for number density, we can use the ideal gas equation, P is equal to NKT. Now you have P, corrected P. Then N is the number density, T is the temperature of the medium. Once you go into this, we can get the P. In the N, sorry. In the case of moon, the temperature is the same as the temperature at the surface of the moon, and their temperature data, surface temperature data of the moon is already available from other measurements on there was a mission called LRO, on which we had a diviner payload called diviner, so which measured the surface temperature. Like from the diviner measurement, the surface temperature maps are available. So we can use the temperature value, substitute here, and then you can obtain the density. So this is one like illustration, like from the raw mass spectrum. Then after quadruple mass discrimination, when we correct for that, and then we apply the correction for the gain. And then finally normalized spectrum. So this is, you can see that we started with -9. Now we have something in the order of -8 in terms of TOR. So these are the this is a summary of whatever we have applied. And after this, the data is called level 1 data. So this is available in Pradhan, where we have applied all these corrections. So now let us see in Pradhan where this data is available. So this is a screenshot of Pradhan, which is the Science Data Archive portal of ISRO. So once you go pradhan.issdc.gov.in, you will see this page where you can click on Chandrayaan 2. Once you click on Chandrayaan 2, this Chandrayaan 2 page open, then there is an access data. Before that, there is some brief description of each instrument, each payload. So you can see for Chase 2 also, they have given some description and the picture of the payload. Now you go the access data, then you can see that all payloads are listed here. So if you, there you can see Chase 2. So once you click on Chase 2, this kind of a page will open where you can find some certain zip files, where the name is Chandrayaan 2, CHA stands for Chase. And this is year, month, day, or hour, minute, second of that data. This is of that particular day. And then that is given here, like a start time, end time. This is basically start time is used in the zip file name. The details of the start, like basically it means that the data in the file starts from this time to this time. And there is some meta information given here, which you can open. Then you can see that, okay, there is some description. These are some common thing. After that, you can see Chase experiment. And then when in case there is any modification, when it is modified, then start time, end time of the data. And then like there are some more information. This is the zip file name. Then you can see what is observing system. All those kind of details are here. So now, okay, after this, after reading the meta information, now you suppose you download. If you click on this, then you download the data. And when you extract, it's a zip file, so you have to extract that. Once you extract, this is zip file, you will extract it to your folder, inside which you find these many data files. There are total 5 files, of which 3 are, you can see from the symbol itself, 3 are CSV file, basically Excel, which you can open with Excel, comma separated files. And these are XML files. These XML files are basically their label files, or we can say meta information. So in this CSV file, there is a file which like CH2, CHA, this for like Chandrayaan 2, Chase 2. Then you can see this HK, this term here HK, this refers to the housekeeping data. All the relevant housekeeping parameters required for the science analysis is put in here. Similarly, a user would like to know what were the operating parameters. For that purpose, OPS, all the operating parameter like mass, range, detector voltage, all information is available here. Then this is the header file, XML file. This will tell, this XML file will tell what is the content of this HK file. Whereas for the another file is which is called OPS, SCI. This is the science data. So the science data file contains basically your mass per charge versus partial pressure for different time intervals. And this is a common meta information file, a label file for operation and operating parameter and the science data. So if you see in detail, this is like this is an example. So there will be basically 1, 2, 3 CSV and 2 XML. So for the science data and operating parameter file, there's a common header file. Whereas for the HK data, it is 1 to 1. And now, in addition, there are certain information needed, like calibration information, like on information on the mass discrimination factors. And there are certain documents. And this one will come into. So that for those details are available in Chase 2 user manual, which you can see on the same page itself. You have this link. If you download this, you can find all the whatever I have described now, all are described here, and different data levels. So then you can start analyzing the data. So now in order to conduct the analysis, you need certain more parameters, which are called the ancillary parameters. Ancillary parameters like what will be needed, like we are making measurements around the moon. So you need to know at what latitude we measured, which was the longitude, and what was the local time, and where was the sun. So solar zenith angle, etc. And location of the spacecraft. All these things are needed. How we can get this information? So these are contained in certain files, which are called spice kernels. Spice, what does it refer will come into? Kernels refers to simply files, spice kernels. And there is a standard library available to read the spice kernel. Once you read the spice kernel and using the library, you can start computing the required parameter. And the spice kernel is in an international standard format. It is like the content of the kernel is like a standard. And this library is available also for different platform like Linux, Windows, and different programming languages like C, Fortran, IDL, MATLAB, like that. Basically, this is developed by a team of NASA called NASA Ancillary Information Facility. So in their website, this library is available. And for each ISRO mission, the spice kernels are provided by our mission team. And this is available when you go to Pradhan. Under other downloads, you can find the spice kernels. Once you have the spice kernels, then you install the spice toolkit from NIF. And then you can use any programming languages of your choice like C, Fortran, IDL, MATLAB. Even in Python, it is available. Then you can start processing the kernel files. So, like these are a few information on a few spice functions I have incorporated here for for a familiarization. Like a spice refers to an acronym for spacecraft, planet, instrument, camera metrics, and events. So this is conventionally this is the way it has now evolved. And basically, it is like there's a spacecraft and you receive the signal on Earth. And we want to know where where was the spacecraft with respect to another planet, you say. So we need to, then that means basically the reference frames changes from spacecraft to Earth. Then we are thinking of another planet. And then where was sun at that time. So all time is a very important parameter here. Everything is tagged with the time. At a given time, universal time. Basically, for that purpose, we use universal time. For a given universal time, where was the position of spacecraft? So basically, spice take care of position, orientation, pointing, etc. Time conversion. So this is what I meant as ancillary data. And then like which is already we have discussed. So there are some information which we should get in the spacecraft, and some information will be based on which certain information will be given from the mission center. And then spacecraft builders also have to give some information on the reference frame of the spacecraft. And our instrument builders have to go where the instrument detector, what is the entrance, aperture for in a given coordinate system. And there are certain planetary constants which is available from organization like IAU. So all these informations are available in certain files called kernels. So these are used in the in deriving the ancillary parameters. So which are the files? There is a certain file called SPK file, which will have an extension of .bsp. B stands for binary, which contains the position of the spacecraft. We call it ephemeris. And then there is a PCK, which is a planetary constant, which goes certain constant parameter about a given planetary body. Then instrument kernel is a responsibility of the one who developed the payload. So they have to provide this information, like in a given coordinate system, what is the viewing angle, those kind of things. Then camera metrics refers to orientation of the spacecraft, orientation of a given body, any given body. And then there is an event metrics, and there are other few like kernels. So using these, you can use, these are some example functions like this function means you have to load the kernel. This first command is to load the kernels. This is like a MATLAB, which works for other this also languages also. And then there are certain functions to find out what is the coverage of the data, then conversion of time to UTC, then get the position of the body, and like this. So using these functions, finally we come to like position of the like basically this function will give you the position of the spacecraft. And then likewise, you derive other like latitude, longitude, altitude, all this information. So finally, then we use the no these parameters for interpreting the data. One more effect which we should take into account is the outgassing effects. We say a mass spectrometer measures whatever ambient gas. So any material in the space, deep vacuum, will start giving out the absorbed volatiles. So in space, we see there are so many joints in any spacecraft or any no, neighboring instruments. They can start giving out their volatiles, and this also will be measured by the mass spectrometer. So that is one of the reason we see even water H2O peak at 18 AMU in space. That is not the lunar water basically. It is like still water was oozing, giving like getting dissolved at that time. So these kind of things we have to tackle before the final interpretation of these volatile gases basically. So you can see that this is the measurement from Rosetta mission. They have almost like a mass spectrometer on a Rosetta mission to Comet. So it's just like 2000 days since launch. You can see that there we can, in terms of pressure, they had a mass spectrometer which measures the pressure. Initially the pressure was high, then it started dropping down, and then asymptotically it is almost like a stable value. So from this to this point, this is a sharp reduction of no, giving away the adsorbed species. Now desorption has reached almost like stabilized, and this is the stabilized background we can say. So anything above this we can above this level we can interpret as signal. This is similar comes from our Mars mission. We can see that there was this was up to we had observation up to here. After that there was a gap of almost a year. Then we had continuous observation till it reached Mars. So this was measured on the way to Mars. So you can see that initially they were dropping out, then drop out, then finally almost like here they are, after that they are going to a steady value. So this also has to be kept in mind while interpreting the peaks in the mass spectrum. Yeah.